Hi everyone, this is coming to you from Education for All. We are looking at problem number 5 or sub question 5. This is a proof in real analysis under completeness axiom. We are asked to show that if the set A and B are non-empty sets with A plus B equal to or less than alpha, for each A in A and B in B, then A and B are bounded above, and sub A plus sub B is equal to or less than alpha. So let's prove. Video number 1 breaks down this question. Try to explain what the question is all about to simplify things. So this is now video number 2 for this proof. So let's carry on. We are given this condition that A plus B is less than or equal to alpha. This is an inequality. Yeah, it's an inequality. And we are told that A is in A belongs to A. That is, these are the elements of the set A. A are the elements of the set A, and B are the elements of the set B. Then A and B are bounded above. We are given this condition already. A and B bounded above. We already told they are bounded above. So we know the definition of bounded above. That is what we're going to use. Before then, we go to the second part, which will be another video. And A and the sub of A and sub B is equals to or less than alpha. So how do we start solving this problem? To show that A and B are bounded above and we have this inequality, we first fix B, this element B, in B for all A in A. This is a trick in real analysis for proofs. For this sort of problems, you have inequality and you have a lot of variables. So you always try to fix one variable. When you fix one variable, that will simplify the problem. So we fixed one element of B. When we fix one element of B for all A, that element will fix B. That element will fix now becomes B. Let's call it B0. I hope it helps. You fix one element, that element, we call it B0C. So now this definition, alpha, A plus B less than alpha. Now, A plus B less than or equal to alpha becomes A plus B, not B sub 0 less than or equal to alpha. Let's stop there. Why do we do this? Why do we fix one element of B and then we'll come back to the original equation? Why do we do that? Am I recording? Yes. The reason why we did this is because from this original equation, you can see that this is a variable. This is a variable. This is a variable. We don't know any of the values of any of these. They're all variables. So how can you work with three variables with an inequality sign? It's not possible. You can't get any answer. You have three variables. You can't get any answer, right? So by fixing one element in one set, and then you try to work out what this is not a variable, this is a constant. These two are variables, this is a constant. Yeah, so it's like they ask you to say x plus y equals 2. How can you find x, the value of x? They want a value for x. You can get x is equals to 2 minus y, but still, what is that? This is still a variable. So that's the situation we have there. We don't want this. We are not going to arrive anywhere. So what we are doing here, by fixing b in b for all a in a, that is, this b now becomes a number. That b is no more a variable, it becomes a constant. And that constant is also valid in this equation. Yeah? What this equation is telling us, if you have a sub 0 plus b sub 0, this is alpha. If you have a sub 1 plus b sub 1, this is less than or equal to alpha. If you have a sub 2 plus b sub 2, this is equal to or less than alpha. A sub n plus b sub n, this is less than or equal to alpha. That is what this statement is telling us. A plus b less than or equal to alpha, a in a, b in b. This is what it's telling us. When you pair them, this is what you get. Anytime you pair two of them, you get this. Yeah? So, now let's go back to the problem. So when you fix this one now you can transform this equation into a is less than or equal to alpha minus b sub naught for all a in a. Don't forget, this is very important, for all a in a. That is the language of proof. Right? So what is the definition of an upper bound? Because we are already told that A and B are upper bound. We just want to prove it. But what do we have now here? Because this is now a number, you now have A is less than or equal to, this is a number, this is a number. So both of them are numbers. They are constants. Now you can find a specific value for A. That is what it is. And then what is this? What is this definition? This definition is the definition for a set being upper bound, having an upper bound. A set having an upper bound. Let me just say upper bound like this. Because the definition for a set to have an upper bound, a set S is bounded above, that is, has an upper bound, if there exists a real number M, such that for every element x in S, x is less than or equal to M. When a set satisfies this condition, every element in the set is less than or equal to a number. That is the highest number of the set. That set is bounded above. So that is what you have just proven here. Right? This is a constant, this is a constant. We can represent it by any constant because they are both constant. They are numbers. When we say constant, it's a number we are saying. We just don't know what the number is. This could be 100 and this could be 10. So 100 minus 10 is 90. or this could be 20 and this is 5. 20 minus 5 is 15. We don't know the particular number. We don't know the value of x, alpha. We don't know the value of b. But they are both numbers, the way we have set the equation. So being that this is a number, we can represent it by another letter by calling that letter also is a number. So we found out that this equation is in fact an upper bound for a. So therefore, we now know that alpha minus b naught is an upper bound. I will just say UP here, please. It's an upper bound, UB, an upper bound for the set for A. Hence, the set A is bounded above. So I've proven that A is bounded above. Now, to show that B is bounded above, we do the same thing. To show B is bounded above, we fix A, the element A, in the set A, for all B in B. This statement, fix A in A for all B in B. Why we say that? We have just demonstrated that earlier on, that the element in the set, they pair up. This equation means the elements, when you take one element in A from the set A and another element in the set B, you add them, then you get this equation holds, they pair up. So if you take A1 from set A and B1 from set A, you add them, this holds. A2 from set A, B2 from set A, you add them up, they pair up. That is what this language is saying. Yeah. So fix A in set A, fix A for all B in set B, so that to say that A and B, they will pair up, right? And secondly, now when we fix A, the moment we fix A now becomes a number. You have fixed it. When you say fix, give it a number, represent it with a number. That is the meaning of fix it. Fix it, represent it with a number. So now this A, since it's a number, A now becomes A naught in A, set A, just like what we say here. Yeah? For all B in B, B in B. So now, A naught plus B is less than or equal to alpha. Because we have now fixed A. So this equation still holds for all B in B. For all B in B. So I need to take off the top side, right? So I take off this one. About this not. So once you have this, and I told you why we are doing this. So take it now from here, yeah? When you have A naught plus B less than or equal to alpha, this now is a number. You have fixed it. So I've given it a number. So now we can do this alpha minus A naught. So this is a constant or constant. Now this inequality becomes simple to deal with. Constant, we can find a value. That value, we call it M if we want You can call it B less than or equal to M. So what is this function here? This is the definition of a set being bounded above. That's the definition. If for every element in the set B, there is a real number M, show that B is less than or equal to M, that set is bounded above. That's what you have proved here. Yeah. So we now state alpha minus A0 is in fact an upper bound. I would say UB, sorry, an upper bound for set B. Hence, B is bounded above. You do like this when you finish complete a proof in maths, you put this symbol to say that's the end of the proof. So that is what you get for this part A. You have proven that set A and set B are bounded above. What we have done here is a simple trick. To prove that a set is bounded above, we only need one upper bound. When you want to prove that a set is bounded above, you only need one element that is higher than the rest of the elements in the set. When you want to do that, it's only one element. For this example here, to prove that this set is bounded above, you only need one element here that is higher than all other elements. What is that one? It's 1. 1 is higher than every other element here because this set is going towards 0. And it's yeah, so 0 is the smallest. As you go towards the left, the numbers keep increasing. So 1 is the highest. So when you have something like this, one element you've proven that is higher than all the other elements, so this set is bounded above. So that is it. When you want to prove that a set is bounded above, only one element you need to show that is higher. And how do you get that assessment? You choose one fixed element. For in this case, we fixed A. That was enough. Assume A is the highest. Now to prove that, to prove something about sub B, if you come now to the second problem to prove sub A and sub B, that is a different case. To prove that, we need a number that is an upper bound for every element of B. For example, if we want to prove sub A, we need an element that is an upper bound for all the elements of sub A. So that will be our next video. Thank you for watching.